For part 2, things get a little bit more complicated. We still have the meter stick, but now we have the position of the lever at, actually let me make this higher so we have a little bit more space to play with. The position of the fulcrum is now at 25 centimeters. So we still have the force due to the center of gravity. Its location is, suppose it's 50. That means the lever arm for the center of gravity is 0.25 meters. 50 centimeters minus 25. We have at the 10 centimeter position, the 200 gram mass. So the lever arm for the 200 will be 25 centimeters minus 10 centimeters, which is 15 centimeters, or 0.15 meters. We have the 20 gram weight and hanger at the 90 centimeter mark. So this is the force due to the 20 gram. And remember, for the hanging masses, we include the hanging mass and the hanger. So for this one, 90 centimeters minus 25, which is 65 centimeters, or 0.65 meters. So we have 3 torques that we can actually calculate here. We have on the left side, actually let me back up. The question really is, where does a 50 gram mass have to hang in order to have our torques equal out? So we have the master equation. On the left we'll have the torque due to the 50 gram mass plus the torque due to the 200 gram mass. Those must equal the torque supplied by the center of gravity of the meter stick and the torque supplied by the 20 gram mass. The only unknown here is the lever arm for the 50. All other variables are really not variables. We know their values. We have enough information to calculate all torques except the torque for the 50 gram mass, and the only thing we don't know about that is the lever arm. So the torque on the 50 gram mass, I'm going to simplify things. It's really more than 50 grams. It's 50 grams plus the mass of the hanger. So we have the 50 gram mass times gravity. I'm making these numbers up. Your numbers will be slightly different. So 0.49 newtons will be the weight of the 50 gram mass times the lever arm plus the torque on the 200 gram mass. That will be 0.2 kilograms times 9.8 meters per second squared times the lever arm for the 200, which was 0.15 meters. This will equal torque to the center of gravity. What number did I make up over here? I said, let's suppose that mass was 60 grams, so 0.06 kilograms. Times gravity, times the lever arm for the center of gravity, 0.25 meters. And on the right side, we still have the third torque due to the 20 gram mass. Times gravity, times its lever arm, 0.65 meters. So this now looks like the second example we had in class. So on the right side, 0.06 times 9.8 times 0.25 plus 0.02 times 9.8 times 0.65. Then we will subtract this quantity right here. We will subtract 0.2 times 9.8 times 0.15. And I typed some numbers in wrong. Fantastic. what I am finding out in my made-up numbers is that, and here is why we have to have the mass of the hangers. If we leave off the mass of the hangers, we will get a negative value for the sum of the right side minus this term on the left. What this negative sign would mean is that the location of this mass has to be on the right-hand side of the fulcrum 4 centimeters away. If I were to divide, I would get negative 0.04 meters. The negative would mean on the right side. This would happen if we forget to actually measure the mass of the hangers. So it is imperative that we have the mass of these hangers added into the weight here, 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 and here. If you do that, the location will actually be on the left-hand side. So suppose we have that done correctly, and I have not done that here to help demonstrate what would happen if we forget that. Suppose that the expected value, which is what we have been solving for here, has a lever arm distance of 5 centimeters. That would mean it's at the 20 centimeter mark. Suppose you actually observed the lever arm distance to be 4.5 centimeters. We could then use those in the same relative error calculation to figure out what the relative error would be. So, in summary, if we look at what is in the table in part 1, we have a number of columns of data. This value I'm circling right here is the torque for the meter stick. This value right here is the weight in newtons of the 200 gram mass. You have to include the hanger. We divide those two to get the expected lever arm. In your table, there is no place to put this. There's only the observed lever arm. The observed is what comes from the table for the mass and hanger. In order to find the expected, take the torque for the meter stick and divide by the weight of the hanging mass. For part 2, we have a slightly bigger table. We have 4 rows, one for the meter stick, which has a torque. The meter stick torque is this one right here. We add to the meter stick torque the torque supplied by the 20 gram mass. These two numbers are all in the right column of that table. Then we subtract the torque supplied by the 200 gram mass and hanger. And then we have to divide by the weight in newtons of the 50 gram mass with its hanger. So we add the two torques for the 65 centimeter lever arm distance for the 60 gram mass. We add to that the center of gravity torque. We subtract from that the torque supplied by the 200 gram mass. Then we divide by the weight in newtons of the 50 gram mass and hanger. All right, I hope this helps with your calculations for this week's Equilibrium Lab. Please email me if you have any questions.